Welcome to the Ritchie School of Engineering and Computer Science. My name is Amin Kodai, and I'm the chair of the Electrical and Computer Engineering Department here at Ritchie School. Very brief about Ritchie School. This building, Electrical Engineering and Computer Science building, is the home to Ritchie School and more than 600 students, focusing on the undergraduate studies and graduate on more than 5 research topics, including artificial intelligence, cybersecurity, smart cities, robotics, and health. As part of the distinguished lecturer series that we have, we invite pioneers in these topics to come to the Ritchie School and share their experience and knowledge with the community. It is my pleasure to introduce today's distinguished speaker, Dr. Seible. Dr. Seible is a former academic VP of Industry Engagement, Dean of Engineering, and Dean of Information Technology at Monash University. Before his time at Monash, he was the Dean of University of California, San Diego, Jacobs School of Engineering, where he was responsible for strategic planning, operations, and school-wide research and education initiatives. He is a member of the US, Australian, and Chinese National Academies of Engineering. Without further ado, please join me in welcoming Dr. Seible to the stage.
Thanks, Amin. Thank you very much, Amin. It's my pleasure to be here at the Ritchie School and in this beautiful auditorium here. I saw it for the first time a couple of months ago, and I was really looking forward to coming back here and to give my lecture today on extreme engineering. So what do I mean by extreme engineering? A lot of times we design our structures just for what we call service loads. Like, I'm a bridge engineer, so I design my bridges for traffic loads, for truck loads, for vehicular loads, for pedestrian loads. But very rarely do our structures fail from these loads. But still, our structures do fail in extreme events. And this is what I'm talking about, to design structures against failure, both against natural disasters, like we have just seen the last few weeks with the hurricanes, or man-made disasters, namely terrorist attacks. And this is what got me excited about my work in structural engineering, namely to realize that structures actually do fail and what we can do as structural engineers to prevent these failures. You can see at the bottom that it's both the Jacobs School of Engineering at UCSD shown and Monash University. I was for 30 years at the University of California in San Diego, and the last 5 years at Monash University in Australia and Melbourne. And so what I show is from both places a little bit, but mostly UC San Diego. When we talk about extreme engineering, really, this is what we want to do, namely designing for the known unknowns. Or you can turn it around, designing for the unknown knowns. Okay, it doesn't matter. But the bottom line is that we don't really know what the loads are on our structure, what we need to design for. Because you give me a certain earthquake, I can always come up and say, oh, there could be a bigger one. You can give me a certain bomb blast, I can always come up with a bigger bomb. Okay? You give me a certain hurricane, and guess what? There's always a bigger one possible, okay? And so really you have to design for something which you really don't know, okay? We know that it's coming, but we don't know what it really is we need to design for. And this is what I mean by designing for the known unknowns. So very quickly, I'm a structural engineer, I'm a bridge engineer, I'm a bridge designer. So this is one of my bridges in La Jolla in California. But I have done my work all over the world. These are not all bridges I designed. I'm not that old, okay? Like the Brooklyn Bridge down there. But I was the chair of the review panel that was put together to strengthen the Brooklyn Bridge against earthquakes and against terrorist attacks. And the same for the Verrazano Narrows Bridge and the upper left. And then we'll talk about the Riona and Tyrion Bridge a little bit later, but I do bridge structures around the world, and in particular when there are seismic or terrorist issues. Most recently, these are some of the bridges I'm still currently involved, okay? You can see all over the world in Taiwan, Long Beach, San Francisco, Canada. So this is what I do. Unfortunately, in natural disasters, our bridges can look like this, okay? And this is what I mean by designing against these kind of loadings that bring our structures to failure. On the left is 1994, the Northridge earthquake in Los Angeles. On the right is exactly 1 year later, 1995, the Kobe earthquake in Japan, okay? But we can also see the same kind of failure from blast loading, okay, from terrorist attacks on our bridge structures. We can see it on our buildings from earthquakes. So these are building failures from different earthquakes. But we can also see it from terrorist attacks, okay? And so this is really what I would like to talk a little bit about today is how can we really design for loads which we don't know what they really are, okay? So ideally, we have to decouple the response of the structure from the loading, okay? That would be the best if any earthquake could be withstood, if any blast load could be withstood, or any hurricane, but that's unfortunately not the case, okay? We can never do that. But looking at the two load cases I want to talk more about today, namely seismic and blast, when we look at really the input which we need for our design, namely the loading time history, we don't know the location of the earthquake, we don't know the intensity, we don't know the duration of shaking, we don't know the frequency content, we don't need any special, know about any special characteristics the earthquake may have, and the same in blast loads. We don't know the standoff, that's the distance from the explosive to the structure, okay? We don't know the charge weight, how big the explosive is. We don't know the type, is it TNT, is it C4? We don't know if it's the modified explosives which we see on television regularly, okay? But I could just as well put a slide up with hurricane loads, because we don't know how far away from the epicenter we will really be with our structure, okay? We don't know beforehand what the intensity really will be when we design our structure. We don't know the wind speeds, okay, which will come and hit our structure. So it's exactly the same thing. And then for all these load cases too, there's an attenuation of the effect. So the best thing against earthquakes is to be far away from earthquakes like you're here in Colorado, okay? So the further you can be away from the epicenter, the safer you are. In blast load too, there's a real attenuation. When you're very close, you feel the full effect. When you're far away or a distance away, then it attenuates, okay, and you don't feel it as much. Hurricane too. If you're not there at the epicenter, at the eye of the earthquake, then it's not quite as bad when you're 100 miles away or so, okay? So when we look at the earthquakes first, this is one of the few still pictures which I really like about earthquakes, where you can see ground shaking in a still picture, okay? Namely, to see the dust coming up from a whole mountain range when the earthquake hits, okay? So you can really see in a still picture the ground shaking, okay? Or we can have big landslides, okay, in earthquakes. Or we can have tsunami effects, and this is very similar then to hurricane effects too, okay? Or we can have fault offsets. So in earthquakes, faults can reach the surface, and they can rupture horizontally, so you have a horizontal offset or a vertical offset. Here you can see a vertical offset, that waterfall was not there before the earthquake. So that's a fault rupture where the surface of the earth really shifts, and that's something we need to design for, and I will show you an example in a little bit. But to design for these events, the best way clearly is to look back and see what has happened in the past, okay? Because that's really the best way for us to learn, okay? But it's a little bit like predicting the weather from yesterday, okay? We can all do that, okay? Because we have experienced it, but to predict tomorrow's weather is a little bit more difficult. So I always use that analogy here. When you drive in your car and suddenly the windshield is blacked out, can you still drive? That's what we're doing with designs by just looking backwards on past experience, okay? So like here we have this straight road, but if we block out the windshield, we just see in our rear view mirror that straight road. And that's a real challenge then to keep driving unless the road stays straight, okay? So here's another example. Here we're just looking in the rear view mirror. There's a city street with cars parked on both sides, okay? And when you look forward, there's a curve coming up, okay? So it's very dangerous just to drive with a rear view mirror, and it's just as dangerous to design just based on past experience. But past experience is extremely valuable. So, and you have seen that again just recently with the hurricanes. They always showed on television these different models, the European model, the US model, and then they had 15 other models, and they showed the predictions, okay? And that's really what half of our business is all about, that we need to try to predict what happens in these known, unknown events, okay? And so we do a lot of modeling, and so you can see here for those who deal with structural analysis with mechanics, it's a finite element mesh using elements for the whole soil condition, then the bridge structure is all modeled, okay? And then we can send earthquakes through our analytical model, and not just one, but many different ones, okay? And that's how these hurricane models also are put together, that we send all kinds of different assumptions through and get the most probable response, okay? So, for example, we start with the fault rupture event, and you can see here, this is the Los Angeles area, San Diego, and then you can see that's where the dotted line is. This is where we will start the earthquake. That's the San Andreas fault, and we have it propagate towards Los Angeles then, past Palm Springs. And let me see if we can get this going here. So you can see here the intensity of ground shaking. These are the kind of things we can model these days. And you can see the shaking spreading out from the San Andreas fault. And even after 80 seconds, after 100 seconds, you can still feel the ground shaking in the Salton Sea and in the Los Angeles basin here. This is a very soft soil. It's like a bowl of jelly, the entire Los Angeles basin. And then in the valley, San Fernando Valley back there, so even 200 seconds after the earthquake, you still see ground shaking, okay? So these are the kind of models which we can put together these days and then use that shaking input as the input into our structures to do the structural design. So for example, bridge columns, okay? This is where we see most of the damage in bridges in earthquakes. You can see here, it doesn't matter when and where, San Fernando 71, 94 Northridge, 95 Kobe in Japan, 08 Wenchuan in China, 99, that was the Ritchie earthquake in Taiwan, okay? So the earthquake always finds the weak spot, okay, in our structures, and then the structures fail. So you can see here, for example, that all these columns here, they have a lot of reinforcement along the column length and very little reinforcement horizontally, okay? So it doesn't confine the concrete. And we know that now that our columns are susceptible to that. Before 71 San Fernando, we really didn't know that. So this is what we learned from past earthquakes. And then what can we do to our existing structures? We cannot just replace our whole bridge inventory from today to tomorrow because we know that the bridges are not designed the way they should be, okay? So we have to go through retrofit programs and retrofit our structures. And you can see here, in California, we developed steel jackets, which we put around all the concrete columns. When you drive on the freeway in California, you will see that there are steel jackets around all the columns, because that provides us now the horizontal reinforcement, which we didn't put in the columns in the first place. And for that, we can do a lot of validation then first in the laboratory. You see that on the left here, a test in a laboratory on a full-scale shorter column, okay? And so really this is what I want to talk about, is because in the end it's not just the prediction, but it's the validation of the assumptions which we use in our analytical models. That's key to it, for us to have meaningful predictions. And for that we would like to have laboratories where we can test our structures full scale, okay? So we build in San Diego, at UC San Diego, the Powell Structural Research Laboratories. And this was the first lab we built, where we can test full-scale buildings up to 5 stories tall and bridges over 100 feet long, full scale in the laboratory. We have a 50-foot reaction wall on the back, a 50-foot reaction wall on the side, and then we use large hydraulic actuators to push the building in the deformation state it would see in an earthquake. Okay? And then we measure the forces required to do that. We measure strains and all kinds of things. Typically, every structure has over 1,000 sensors put in. And those are the measurements we use then to calibrate our analytical models. Okay? So to do large-scale testing, there are 3 key principles which we need to follow. One, it should be done under controlled laboratory conditions, that we really get quality data. In order for us to validate analytical models, we need to have clean data. And so we need to measure parameters which we can then adjust in our analytical model. Okay? The next thing we need to do is we need to test either at large scale or ideally at full scale, because that's the only way to get realistic damage patterns and failure modes. A lot of times we see structures being scaled down to little scale models, okay? And they're being put on a shake table and send an earthquake through, but you do not get this correct damage patterns and not the correct failure modes, okay? So, for example, concrete structures, you can only scale a certain amount, maybe a third or a quarter scale. Anything less than that, the reinforcement isn't there anymore. The aggregates in the concrete are getting too small, so you get completely different behavior. So you should test full scale, ideally. And then the test should be performed under realistic load simulations with test protocols which simulate the actual demands. For example, testing bridge columns in the laboratory. Looking around the world, and we started out that way too in San Diego, that you have a column and you have it full scale and you're happy that you can do that, and then you take the column, push and pull and push and pull, push and pull with larger displacements until the column fails. And guess what? It's like the coat hanger effect. When you have a metal coat hanger, bend it back and forth, low cycle fatigue, eventually it breaks, okay? We have never seen low cycle fatigue in a real earthquake, okay? Because you may get 1 or 2 large cycles, but not 50 or 100, okay? And so then the test in the laboratory becomes meaningless, okay? When you test with load input, that doesn't correspond to the real world, okay? So when you take these 3 theses here and develop then a research program around it, what that means is that you need a shake table where you can put full-scale structures on the shake table, send real earthquake ground motions through. And so we built in San Diego then the world's first and only outdoor shake table, okay, where we can put structures of 2,000-ton payload, okay, on that shake table. And we tested 5-story buildings, 6-story buildings, 7-story buildings now on the table, and we reached about 1/3 of the capacity of the table, okay, so we can still test much, much bigger structures. So, for example, one of the first structures we tested was a windmill, okay, 30 meters tall. Okay, so when you test that structure, it's very easy to lift it on the table with a big crane, bolt it down on the table, and it can send earthquakes through, okay? You can do that at no other facility worldwide. Yes, we have big shake tables, but they're indoors, okay? And then you can never put a full-scale structure on these tables, okay? Or here, a 3-story parking structure. So that's a precast concrete parking structure. Yeah! And you can see our students have a lot of fun in San Diego. Or here, a 5-story reinforced concrete shear wall. What happened to the sound? Well, doesn't matter. So you can see here how the building is shaking, and then when you take close-ups with the camera, you can see how every crack opens and closes like the building is breathing under the earthquake load, okay? Let's take a look at bridges. This is the Coronado Bridge in San Diego. And it was built in the late 60s, 68, 69, and clearly to seismic standards which are different from the ones we have today. And then when we went back to our seismologists in terms of what we can expect in the Coronado Bay in terms of earthquakes, they told us there's something called the Silver Strand Fault. And the Silver Strand Fault can have surface ruptures of up to 1 meter or 3 feet horizontally during the earthquake. And so we had to design then the seismic retrofit that the bridge can take a horizontal fault offset of 1 meter or 3 feet and still undergo the full earthquake motion. The only thing our seismologists couldn't tell us between which two piers that fault rupture would occur. And so we have to design the whole bridge that between any two piers we can have that 1 meter offset, okay? And so design then consisted of putting on top of the pier seismic isolators, big rubber bearings or elastomeric bearings, about 1 meter tall, okay? And the whole idea is that when you have these soft bearings on top of the pier, that the earthquake comes and shakes, okay? And the pier doesn't even know, the bridge doesn't even know that there's an earthquake because you have that soft rubber in between, okay? Also, that soft rubber can deform by up to 1 meter, okay? And so in order to retrofit the bridge like this, Caltrans said, this is great idea, but how do we know that it's working? So, well, then we had to design a separate laboratory again for these kind of tests, namely a seismic response modification device system that can take these devices through very large displacement, 8-foot displacements, okay, with loads up to 12 million pounds, okay, on these bearings, right? And so you see a schematic of the test setup here, and this is one of these bearings now in the test setup. So you saw 100% deformations, namely the height of the bearing applied horizontally, okay? These bearings can go through 300% deformation before they fail, okay? So this is the retrofit of the Coronado Bridge, that in the earthquake comes and shakes, or even if we have fault of that, then the pier goes there and then shakes over there, okay? So this is how we decouple the structural response from the input, okay? So even if we have a bigger earthquake, I'm not worried about it, okay? It will be fine, okay? So I don't really care anymore what the earthquake is in San Diego, okay, for the Coronado Bridge. Now we come to the Riona and Tyrion Bridge. That's the world's longest cable-stayed bridge with over 3 kilometers in length, okay? And the initial design was that each pier, the superstructure, the bridge was connected at the pier, and then there were hinges between the individual spans, but it became a very flexible system. And I was responsible for the seismic design of the Riona and Tyrion Bridge across the Strait of Corinth in Greece. And again, very similar to California. We can expect the same magnitude earthquakes there in Greece, and we can also expect fault ruptures and offsets. And so the idea was now not to isolate the bridge with bearings, but to just hang the bridge from the supports and let it float freely between the towers, okay? So you can see here, the towers have 4 legs. The bridge is just supported by the cables. It's not connected to the tower. And so it's the same idea, just reversed, namely that it's hanging down, okay? And is isolated from the seismic input. In order to do that, you need clearly then, and we connected the whole bridge end to end without expansion joints. Usually you have expansion joints in bridges every 300, 400 feet. That's what you hear when you drive across a bridge, you know, it goes, ka-thunk, you know. Those are the expansion joints. Here we needed an expansion joint then at the end of the bridge, which is 3 kilometers long, of 1.5 meter expansion joint on each side, okay? So the whole bridge is free floating end to end, just supported by the cables. But then we put dampers in. What are dampers? Well, it's like shock absorbers in a car, okay? These are oil-filled dampers which dampen then any motion, which are relative motion between the tower and the bridge superstructure. And so these are these huge blue dampers, shock absorbers, which we put in the bridge at every pier. But again, dampers of that size had never been built in the world or never been tested, okay? But we in San Diego could put it in our seismic response modification device system and test it under simulated seismic loads. So there's over 281 tons of force being put in these dampers, okay? And it's very difficult sometimes to envision what are 281 tons, you know? I always think back to my first car, a Volkswagen Beetle, okay? It weighs about 1 ton, okay? So it's 281 Beetles, okay? That's the force, okay, in these dampers then. Now the other thing which we did with that same loading system has nothing to do with bridges, but with the 787 Dreamliner, because it has an all-composite landing gear, okay, carbon composite landing gear. And this strut here, the landing gear brace, was never clearly tested to failure and couldn't be tested to failure anywhere. So Boeing came to San Diego and said, can you test the landing gear for the 787 Dreamliner for us? And there you can see it in the test setup then, okay? And it performed beautiful. It's all, this white element, there's all carbon composite, okay? It's the first time that a landing gear is not built out of steel or aluminum, high-strength aluminum, but out of carbon composites for weight purposes. So let me now focus a little bit on the terrorist attacks and the blast loading which we get on structures. This work was done, and you see in the bottom right the logo for the DTRA, or the Defense Threat Reduction Agency, okay? And they have a test stand at White Sands in New Mexico, right at the Trinity site at Ground Zero. This is where the big test site is, and where we can build then 5-story full-scale buildings and do real field blast tests, okay, to find out how can we then strengthen our buildings against blast loads. So this was one of the first tests on it's a reinforced concrete frame with masonry infill. And you can see the building is still standing. When you look at it, the target was the center column in the middle on the ground floor there. You can see how deformed it is in the two right pictures. On the left, you see what the building looked like before the blast load. So it's a concrete frame with masonry wall infills. And you can see that while the building is still standing, the masonry walls are blown clear through the building, okay? So unfortunately, in this case, even though the building is standing, everybody in the building would be dead, okay? And so we have to think about several things. One, how can we keep the building really from collapsing? That column is very close to gone, and so when we take out that column completely, the building may collapse, okay? And then how can we keep these masonry walls in place, that they don't fly through the whole building, okay? So we developed then, again in San Diego, hardening systems using carbon fiber wraps around our columns, okay? And we developed that first for earthquake loads. Just like we put steel jackets on, we can also wrap our columns with carbon, okay? And it worked really fine, and this is why DTRA then came to us in San Diego and said, look, you're doing the seismic retrofit, which seems to work really well. Can you do the same for blast? And naturally we said, oh, sure we can, you know, so no idea what we were talking about, okay, at the time. So we wrapped that column, that same column, it was rebuilt. The whole building was rebuilt, all the infill walls were put in, and that column was wrapped with carbon fiber. And then the same test with the same charge load was repeated. And this is what the column looked like after the test, okay? Perfectly straight. You can see just at the very top, the carbon jacket opened up, okay? So that was the first indication that retrofitting or hardening of structures using carbon fiber confinement could be very effective. At the time, we had no idea how many layers of carbon we needed and so on, you know. And so we developed a whole test program then. We developed a separate column test stand at Kirtland Air Force Base in New Mexico in Albuquerque. And you can see on the left, these are then real field blast tests again. On the left, you see a column that has not the retrofit, is not hardened, an S-built column. On the right, you see a column that has a carbon jacket, okay? And again, the column on the right is almost perfectly straight. The column on the left, you see the typical failure modes, which we would expect in a blast load case, okay? And so we did numerous blast tests there at field tests at Albuquerque, but several times we couldn't do the test. So you fly out to Albuquerque and then you're told, oh, there's an inversion layer and that's because why we cannot test today. Then you fly back. As soon as you're back in San Diego, they tell you, oh, you can test now. Okay, so have to fly back. And the other time where we went out there was on 9/11. We were in the hotel in Albuquerque when we see the World Trade Center being hit. And then we went to the Air Force Base, and they had already the armored vehicles out there pointing machine guns at you, and so we're out of here, back to San Diego. But we wanted then to test these columns in San Diego and not in New Mexico. But unfortunately, they didn't allow us to use explosives on campus. And I don't know if they would allow it here at Denver University. But we decided then to try to build a test setup, the world's first blast simulator, where we simulate blast loads in the laboratory using servo-controlled hydraulics and not real blast loads, okay? And so you can see here, this is the schematic, 4 servo-controlled hydraulic actuators with red steel plates on front, and then these turquoise elastomeric pads, which impact then an impulsive force on your column and then pull immediately back, okay? And then you can program these actuators to have a different force distribution, not just uniform, whatever you want, okay? So this is the first test then in that blast simulator.
1, 0.
And you can see the same damage patterns which we saw on the columns in the field blast test in Albuquerque. But the real value comes in when we use high-speed photography on these blast tests. In a real blast test, all you see is the fireball. You don't see what happens to your structure. Like in the first blast I showed you on the 4-story building, you just saw the fireball, and then you have to wait until the dust settles, and then you can see what happened. And clearly for analytical models, we would like to see exactly what happens during the blast, how the cracks develop and how the concrete spalls off. And when you look at that, yeah, that's working. This is on a masonry wall then, unreinforced masonry, okay? The impact, these are taken with phantom cameras, 20,000 frames per second, okay? And now you can see how every piece is falling apart. And this is how a masonry wall, just like in the 4-story building, would fly then through the whole building, okay? We do then analytical models, clearly, which simulate this, okay? So these tests, since they're full-scale tests, you never do 10 or 20 of the same kind. You typically do 1, okay? And a one-of-a-kind test is statistically absolutely meaningless, okay? Unless you have an analytical model, which you use then to predict the test and then to validate afterwards with the test results. So here you can see the masonry wall. What we did then as a first solution, we sprayed it with polyurea on the back, on the inside, okay? Polyurea is the same stuff you use for truck bed liners or so, you know, it's a spray-on foam, okay? And there we go. So you can see how the wall deforms and the polyurea holds the wall together. But then, unfortunately, you can see at the top and bottom, it also pulls off the ceiling, it pulls off the floor, and then the whole wall still comes in, okay? And will definitely kill you, okay, when it comes at you as a single piece. And that's the same we saw hardening of windows, okay? Like I was involved in hardening a lot of our embassies worldwide, and all the windows in embassies have a mylar film on top of it, because when the window gets hit with a blast load, then it would fracture in these millions of pieces and hurt you. And now we put a mylar film on the window so it stays together, okay? But the problem is that it stays together at one big piece and comes flying through the room and definitely kills you, okay? And so we had to design then for the Defense Threat Reduction Agency systems that catch the window. So for example, you put a steel bar in the middle of the window, and then the window comes and folds around it, okay? And so very similar here, we have to come up with methods to catch that whole wall. So you can see on the right, we have dowels into the ceiling, and then ductile connectors, so just steel straps, okay, Simpson ties basically, that then elongate when the wall comes in. And there you can see then the wall with the ductile connectors at the top. You can see the deformations of the wall, and then it stretches at the connectors at the top, but the connectors hold it back. And here in the picture, you see pieces flying around it, but in a building, you couldn't have that. You know, you would have the columns and the wall. But overall, the wall stays in place and doesn't fly through the whole building. Okay, let's look at bridges a little bit more broadly. You can see here the San Francisco Oakland Bay area with the Golden Gate in the back, the Oakland Bay Bridge, and then the new San Francisco Oakland Bay Bridge at the very bottom. And that's what I want to focus on a little bit more because it's a unique structure. But overall, we have 24,000 bridges in California, and we spent in the last 20 years about $16 billion to harden or retrofit our bridges against earthquakes and against terrorist attacks, okay? So, and all these hardening or retrofit technologies are based on the work which we did in our laboratories in San Diego. And then we have something called the Caltrans Seismic Advisory Board. And after the '89 Loma Prieta earthquake, we wrote a report competing against time to assess why bridges failed. And then in '94 Northridge, we had again damage of bridges. When we wrote the report, The Continuing Challenge. And then we didn't have any major earthquakes since, and people are becoming complacent. They say, oh, we don't need to worry about it. We don't have a big earthquake. It's just like when you don't have a big hurricane for a few years, then you become complacent. So we wrote interim reports, the race to seismic safety and closing the gap, and now we are just working on another report as we speak. So the San Francisco Oakland Bay Bridge, the new one, is a very interesting structure, namely it's a self-anchored suspension bridge. What does that mean? In a suspension bridge, typically the way you build a suspension bridge is that you build the towers, and you build the big anchorages at the end. You put the cable over the towers and anchored at the end, and then you pull the steel segments, the superstructure, up individually and connect it, okay? Here you don't see any big anchorage at the end of the bridge, okay? So it's a self-anchored suspension bridge. It's the cable coming from the tower, wraps around the end of the bridge, and goes up on the other side, and then it's anchored again in the bridge itself, okay? So the question is, how do you build a self-anchored suspension bridge? We'll come to that a little bit later. But you see in this picture here, this is the reinforcement which we have in some of the piers, okay? And you can see now the difference from some of the columns we saw in earthquakes before. Now we put horizontal steel in, confinement steel, okay? So we don't need the steel jacket on the outside, we have it on the inside. But now we have a different problem, because the contractors come back and say, yeah, you put so much steel in your design, we cannot build it anymore, okay? So we call it the canary test, you know? If you can put a canary inside the cage and it can escape, then there's enough room for the contractor to build it, okay? But we have another method, and this is what we did then at Monash University in Australia, in Melbourne. We have the world's largest cave a computer-aided virtual environment where you can walk through your 3D data set and interrogate it visually. We call that visual analytics. So here we have, like when you're in a 3D movie, you think there are things flying out at you, like to grab it. Here we have not just one 3D display, but 80 3D displays around you in an 8-meter diameter circle, and they throw 3D images at you, okay? And so really you stand in your data set, okay? And then it's getting tracked based on your position, so you can walk through your data set, okay? And so here you can see, you can stand in your reinforcing cage, you can make sure that there's no construction conflict. You can tell the contractor, no, it can be built. This is the way you have to build it. There's no conflict, okay? So it's for construction conflict resolution. And it's not just for one person. You can have groups of 10, 15 people in the cave, and they all experience the same 3D environment. So this is what we call visual analytics, that you really walk through your data set. So here you can see how a self-anchored suspension bridge is built. You can see the tower. You can see the superstructure, which has to be built on temporary piers, okay? Because you need the bridge structure to anchor the cables, okay? And then you lift the bridge structure when you have the cables. There you can just see the placement of the cables. These are the catwalks. The cable is not even in place. And then you put on the vertical hangers. So this is the construction then of the cables. And then the vertical hangers, you lift it off the temporary piers, and then you take the temporary piers out, okay? But the net result is that your whole bridge deck is under a very large compression force. Namely, the full cable force is anchored in the bridge deck. So it goes through the bridge, okay? So it's a closed force system, okay? So this was the opening of the bridge 4 years ago. That's the last inspection, and then the first vehicles going over the bridge. But we're still working on some of the last details, even so the bridge is open for traffic. But some of the details in the tower we are still working on. But the problem was that somebody made a comment on television, and it was one of our learned colleagues from academia, that this bridge would collapse because of this big compression force if it's just a small blast load on top of the bridge. If you punch a hole in the bridge, and then the bridge would collapse in itself, buckle, okay? And so clearly Caltrans could not leave that just standing there. And so they came to us and said, what can we do, okay? So we did a lot of analytical work, okay, by removing sections of the bridge deck, as you can see here, putting the full axial load on it. And we didn't see really any way this bridge could fail, even when you remove the full deck. But that's not good enough. You have to show that to people, okay? They don't believe necessarily just in your analytical models. And so we built then a full section of bridge deck. So the whole bridge consists of 90 of these bridge deck sections, okay? And we built one, overlaid it with 2 inches of asphalt concrete, just like the Rio bridge deck. Took it out to China Lake Naval Air Station, pre-stressed it, put the preload on, okay, with pre-stressing cables on the side, put a K-car on it, loaded the trunk with 4 boxes of flake TNT, okay, and then tested it.
4, 3, 2, 1, mark it.
Power off, yellow out.
Sequencer D.
Sequencer off.
We got a detonation, power's off.
And that was the result. Just a small hole in the bridge deck, about 2.5, 3 feet diameter, okay? And the deck did not buckle, it was still there. So the most common explosive, which you can think of, clearly I can always think of a bigger explosive, as I said before, but the most common one would be a car where the trunk is loaded with explosives, okay? So the bridge definitely would not collapse. So we did another test on the same deck. So 2 tests in a row, same failure mode. And so this is data which is archived at Caltrans. It is not really public knowledge, okay? but they will pull it out when somebody comes and asks them, are you sure that there is no danger of terrorist attacks on the Bay Bridge? We did then further tests on all kinds of different bridge decks, concrete bridge decks, not just the orthotropic steel deck which we had. This time we didn't use K-cars anymore. Okay, we didn't have enough cars, so we just built a little stand, the same standoff, which it would be in a trunk, and we used C4 or plastic explosives for that. Okay. And then we did different charges, 25 pounds, 50 pounds, 100 pounds. You can see here the damage you see, and the interesting thing for those of you who don't know concrete behavior is that at the top you see less damage than at the bottom of the deck, because concrete is only a compression material. It's good in compression. And so at the top you see just discoloration with 25 pounds and big chunks already pushed out at the bottom. And then at 50 pounds, the hole at the top is less than at the bottom, and so on, you know. And so this is the kind of database we established then experimentally. And then we developed analytical models which show exactly what we did experimentally. It's always easy for a good analyst to predict the weather from yesterday. Okay. So you can see here that it looks just exactly the same after we did the test. Okay. Okay, let's come now last to some of our more landmark structures, because again, terrorist attacks typically are not being against our common structures, but at landmark structures. Okay? And so we had several threats against the Golden Gate Bridge or against the Verrazano Narrows Bridge. And then what can you do? The biggest defense against bomb blast, as we discussed at the beginning, is to have the standoff. The further you're away from your blast load, the better. But on a bridge, you cannot have a standoff. Otherwise, you would have to close all the lanes for traffic. Okay? So it's very difficult. So we have to deal with close explosive blast loads against these bridge towers. So how are these bridge towers built? They are not solid steel. Okay? They are cellular structures. Okay? Cells about 1 meter by 1 meter, 3 feet by 3 foot cells. Okay? And then bolted or riveted together. You can see me here crawling through one of the cells in the Verrazano Narrows Bridge. Okay? And so this is what we needed to understand. And how do these bridge towers fail? So the first thing is we took a 6-inch steel plate, just like the thickness of these tower faces, and we put it into our blast simulator. And you can see here how that fails, how the bolts are being broken then, and the steel plate deforms. And again, we can develop analytical models which in the end show the same. Okay? But it's not just this one single steel plate. We have then these multi-cells, okay? And so we did a lot of analytical simulation that was not done just by us in-house, but by some of the big companies that do blast analysis. And they showed us these examples where the blast hits the first cell, and then it fractures into lots of little fragments, and then they act like projectiles and damage the second cell, and then the next cell, and the next cell. And the only question I ask is, how do you know that these are these small little 2 by 2 inch pieces? Okay? And the answer I got, well, this is the discretization I used in my model, the finite element mesh. Okay? And so we decided we better test that in the field to see if that really happens, that fragmentation. And so we built just a 3-cell structure, again put flake TNT on the middle cell here, and did the field test, as you can see here. And again, during the test, you don't see anything. You just see the big fireball, okay? And then you wait until the dust settles, and then you see the result. And we were very surprised to see these results. Yes, we only saw damage in the middle cell where the blast load was, but you see on the right these big pieces of steel that were cut out, okay? You see the hole on the left there. And so we term them flyer plates, because these plates are being cut out and then fly into the next cell, cut in a hole, fly in the next cell. It's a little bit similar to our building with the walls, where you put something behind, you get a big piece then, okay? So here we get flyer plates, and then clearly after we saw that in the test, again, we could model it analytically too, okay? So these flyer plates that develop and then poke a hole in the next cell. So what do you do against this kind of failure behavior, okay? So we developed then what was called KEDs, or kinetic energy defeat devices. So what is that, a kinetic energy defeat device? Well, you can see on the left just little polymer tubes filled with sand, and on the right, you all know what that is, water bottles. We just filled it with red water that you can see it better, okay? And the whole idea is to divert the energy. In the left with sand, it will go straight through. When you have these water bottles, they break and the energy goes partially off to the side, okay? So here you can see the test with the sand-filled ones. And it goes straight through and the plate is being pulled out, okay? And then on the right, you can see the test with the water bottles. And you can see the energy going to the side, okay? And the plate was still in place after the test. Okay? And so that simple principle was then translated into the real case. So this was done again in New Mexico at Emmertech, at New Mexico Tech. They have also a big blast test area there. And you see a 3-cell mock-up, similar to what we have in a big bridge column tower. In the center cell, we put PVC tubes filled with water, these KEDs, these kinetic energy defeat devices. And then we overlaid the whole thing with 2 inches or 3 inches of C4, okay, of plastic explosives. And then we did the test. The reason why this picture is so dark, C4 explosives are very bright when they go off, okay? So you really have to close the aperture of your camera. Otherwise, in the end, you don't see anything, okay? So you can still see the outline of the structure there. And there you can see the C4 going off. And we thought initially, well, that's it, you know, with high-speed cameras. But then we saw an amazing effect. Focus on the 2 outside cells now, okay? You see the big fireball, and there you can see these flyer plates flying through, okay? So for the very first time, you could actually see that really visually what happens on a cellular structure when real blast loads are applied. And the center cell is in perfect intact, okay? So no damage to the center cell. So I cannot tell you what we did to strengthen our bridge towers, okay? I just show you some of the research which we did in support of it. So anyways, look, I think I talked enough. So this is a little bit designing for the known unknowns. And I thank you for your attention. And I'll be more than happy to answer any questions. Yeah.
When you design a bridge, those water tubes in there?
Yeah.
How do you compensate for the extra weight?
Oh, it's so little compared to the weight of the bridge. It's nothing. Yeah. Sure.
The concrete bridges versus the composite bridges, which one would accept or tolerate a bigger blast? This is the question you'd be asking the composite people.
Well, does any one of you want to answer?
They just started with the like this.
Now look, the answer is in the end, if it's designed right, any bridge can withstand it, okay? You saw that composites can be very useful in hardening of existing structures, but we can design existing concrete structures from the beginning already in the right way, okay? It's just that when we learned about these confinement effects in earthquakes first, but then in blast loads, that was after the 71 San Fernando earthquake in California, and already 75% of our bridges had been built. So we cannot just say, look, forget about those, okay, and we rebuild it all with composites. We actually built an all-composite bridge in California on State Route 89 next to the Salton Sea. It's just a two-span, what I call a ditch crosser, okay, not a major bridge, but it's carbon shells filled with concrete, overlaid with a fiberglass deck, okay? And that bridge was in service for close to 20 years until they recently took it out because it was too lively, meaning the deflections were really big. Big trucks drove over it and they started bouncing, okay? And that's the big issue when you design with advanced composites. You have no strength issues with these composites. They're so much stronger than our steel, okay? But it's a stiffness issue. It's all deformation controlled. So when you design with composites, keep that in mind. It's deformation controlled, okay? It's all strains, okay, which you have to look at, not stresses. They're typically strong enough to take any load, okay? Yeah?
Yeah, I'm wondering, in your experiences here, what's the impact on cost of building these changes?
Yeah. No, for concrete bridges to design them right from the beginning with a little bit more horizontal steel, that's about 1% to 2% cost increase, not more, okay? When you build a bridge out of concrete versus this carbon bridge, which I just described, that was twice as expensive as the concrete bridge, and that's why we don't see more of it, okay? So the advanced composites are still more expensive. Unfortunately, our common construction materials are literally dirt cheap, okay? Yeah. Yeah, yeah. I showed you that one picture of the Bay Bridge during construction of one of the concrete piers. Let me just pull it up again. You see, this is what typical columns look like now. That in terms of, we call it reinforcement ratio. That's the steel amount compared to the concrete volume. You have the same reinforcement ratio vertically as you have horizontally, okay? Mm-hmm. Typically 1% to 2%, okay? Yes? Yeah. Well, the answer to that is still out, you know. We don't know, really. We haven't opened any of these steel jackets yet, even so we have installed them now for over 20 years, okay? And so we don't really know what the concrete does inside that steel jacket. But it is grouted, you know. You put a jacket around, then you pump grout in to get a solid connection between the steel jacket and the concrete. And so there's really no reason why it should deteriorate, okay? And so the answer is probably yes, it can extend the service life. Yeah?
So also these problems you had to like build a full-scale test fixture.
Mm-hmm.
What was like the time frame for some of those building those laboratories?
Well, look, the best example is that SRMT test system where we tested these big bearings. That system alone cost $15 million, okay? And it was about a 1-year design frame, another half year to build it. And then since we had to control 13 servo-controlled hydraulic actuators simultaneously, it took us over 2 years to get control over that beast, okay? So it can be a very long time frame. But when you think about an expenditure of over $16 billion to retrofit bridges, 15 million is just noise level, okay? And a lot of times our tests follow the actual construction, okay? So the structure is built and then we do what we call a proof of concept test afterwards to show that yes, it is safe, okay? Because the construction, you cannot stop the construction, you know? Otherwise costs go through the roof. And so that's the worst thing we can do in academia, to hold up a big construction project. But we can still show after the fact what the real response would be. So some of these tests are very expensive and take a long time. Like each of these full-scale building tests on the outdoor shake table is typically $4 to $5 million, one test. Okay. Mm-hmm.
Why not using dynamic bosons, you know, this size factor predictions and simulate these under laboratory conditions instead of doing, you know, this full-scale testing, which is so extremely expensive?
Well, as I said, in the end, you can only scale so much, okay, with real construction materials, okay? As long as you stay in the elastic range, perfectly fine, but that's not what we're interested here. We are looking for actual failures and actual damage patterns and then actual repairs, okay? Typically, all the structures you saw, all the tests, we don't just stop there, we repair it again and then test it again to see how effective repair measures are, okay? And for that, you have to do it full scale. And that's what the Powell Structural Research Labs in San Diego are for. They are the world's largest structural testing facility and also the world's busiest. I know all the other big laboratories around the world, and they do maybe 5 or 6 large-scale tests a year, and we do 2 per week in San Diego on average. Okay? So it's no comparison. Yeah?
That rubber bushing that you had,
Mm-hmm.
where it was extending and
Mm-hmm.
moving back and forth, was the formulation for that rubber, was that
It started out,
shelf, or was it?
no, it started out with natural rubber, okay? And then in the meantime, we also lose elastomeric bearings, you know. So you can still get both rubber bearings and elastomeric bearings. The elastomeric bearings are supposed to last a little bit longer, but again, the verdict is still out, you know. The longest living isolators, they were first built in Japan. They put big buildings on these isolators, and they're about 40 years old now. Okay. Mm-hmm. Yeah. Okay, yeah.
On those isolators in the Coronado Bridge, you had the bridge built and then realized that if a 1 meter split happened, it would destroy the bridge. How did you install those isolators on the bridge after it had already been built?
Yeah, well, you got on top of the pier, you checked up the bridge with big hydraulic checks, you took out the old bearings, which were big steel bearings, okay, rocker bearings, because there it was only designed for one direction, okay, and then you put in these elastomeric bearings, and then you lower the bridge again on top of the bearings. You do that pier by pier by pier under full traffic, okay. We are not allowed to close the traffic.
Let them know, hey, we're looking upwards a bit more this time.
No. Look, again, when you have bridge spans that are 200 feet long, okay, when you lift up the bridge by 2 inches, nobody notices that, okay. Yeah. Okay? Yeah?
How many of those bearings are on each pier?
4. There are 4 bearings on each pier. Mm-hmm. Yeah. Mm-hmm. Now I need to take you out to the Coronado Bridge one of these days. You can walk the bridge. I always took my classes out there, my students on top of the Coronado Bridge, climbed out on the pier. Always was a lot of fun. Okay? Well, again, I thank you very much for your attention.